For centuries, humanity has watched objects cross the night sky. Most are familiar. Planets follow predictable paths. Asteroids pass through the solar system. Comets return on long, repeating orbits. But occasionally, something arrives from somewhere far beyond our solar system. That is what makes 3I-ATLAS so fascinating. Discovered in 2025, 3I-ATLAS was identified as an interstellar object, a visitor that originated outside our solar system and is simply passing through. That alone makes it extraordinary. Only a handful of confirmed interstellar objects have ever been identified, meaning every new one gives astronomers a rare opportunity to study material that formed around another star. At first, there was no reason to assume that 3I-ATLAS was anything other than a natural comet. Its appearance, activity, and trajectory could be investigated using the same physical laws scientists use to study other comets. But interstellar objects are difficult to observe. They move rapidly. They are faint. And we have only a limited amount of time to collect data before they continue their journey back into interstellar space. That makes every observation valuable. One of the most important questions is simple: where did this object come from? Astronomers can reconstruct its path by measuring its position against background stars over time. Using those observations, researchers can calculate its orbit and determine whether the object is gravitationally bound to the Sun. In the case of 3I-ATLAS, its strongly hyperbolic trajectory indicates that it is not a normal solar system comet returning from a distant region. It came from outside. And it will leave again. That fact alone makes the object scientifically important. But then comes another question. What is it made of? When sunlight interacts with gas and dust surrounding a comet, molecules can absorb and emit specific wavelengths of light. Spectroscopy allows scientists to identify those chemical signatures. This is how astronomers can study an object that is millions of kilometers away without ever touching it. Observations of 3I-ATLAS have provided information about its coma, the cloud of gas and dust surrounding its nucleus. Different gases can dominate at different stages of a comet's journey. Carbon dioxide, water, carbon monoxide, dust, and other compounds can all contribute to its appearance and activity. And because 3I-ATLAS formed around another star, its chemistry may provide clues about how planetary systems elsewhere in the galaxy produce comets and other small bodies. This is where the story becomes much bigger than one object. Our solar system contains billions of icy and rocky bodies. But until an interstellar visitor passes through, we have no direct sample of material formed around another star. 3I-ATLAS is effectively a natural messenger from another planetary system. We do not know exactly which star system produced it. And because it has traveled through interstellar space for an unknown amount of time, its journey may have been incredibly long. Imagine an icy body forming around another star billions of years ago. Its planetary system changes. Its original star evolves. Gravitational interactions eventually eject the object. Then it begins drifting through the space between stars. For millions or perhaps billions of years, it travels almost completely alone. Eventually, its path intersects with our solar system. And astronomers happen to be watching. That is the remarkable coincidence behind every interstellar visitor. Now, what about the rumors that 3I-ATLAS could collide with Mars? This is where the distinction between scientific observation and online speculation becomes extremely important. Astronomers calculate trajectories using observations and gravitational models. As additional measurements become available, the uncertainty in an object's future position can be reduced. But a changing estimate does not mean that an object is suddenly being steered. Natural comets can also experience non-gravitational forces. When sunlight heats an icy body, material can escape from its surface. Those jets of gas can produce a small reaction force. Over time, that force can slightly alter the object's trajectory. This phenomenon is real and has been observed in ordinary comets. So if an interstellar comet experiences changes in its motion, scientists first investigate natural explanations. There is currently no established evidence that 3I Atlas is under artificial control. There is also no scientific basis for claiming that it is sending a coded message through its trajectory. Those ideas are interesting as science fiction concepts, but they are very different from confirmed astronomy. And that distinction matters. Because the real story is already extraordinary enough. An object formed around another star has entered our solar system. Human telescopes detected it. There is something deeply strange about studying an object that does not belong to our solar system. Every planet, asteroid, and comet we normally observe was born within the same broad cosmic neighborhood. 3I Atlas is different. Its journey began somewhere else. That makes it more than another comet. It is a sample of another planetary system, but a sample we can only study from a distance. Astronomers can learn about its physical properties by observing how it reflects sunlight and how its surrounding gases emit light. The coma surrounding the object can reveal which volatile compounds are escaping from its surface. Its dust can provide information about the solid material trapped inside. And its behavior as it moves closer to and farther from the sun can tell scientists how its surface responds to solar heating. These observations may eventually help answer one of astronomy's biggest questions. Are planetary systems built from the same basic ingredients? We know that planets form around stars. We know that disks of gas and dust surround young stars. We know that comets and asteroids can preserve material from the early stages of planetary formation. But we have never had many opportunities to directly study small bodies from another star system. Interstellar objects change that. They allow us to compare distant planetary systems with our own. Imagine discovering that the chemistry of 3I Atlas closely resembles the chemistry of comets in our solar system. That could suggest that certain ingredients are widespread throughout the galaxy. But imagine the opposite. Suppose its composition contains unusual ratios of molecules or minerals that are uncommon in our solar system. That could provide evidence that planetary systems develop under a much wider range of conditions than we previously understood. Either result would be scientifically valuable. And there is another important question. How do objects like this escape their original planetary systems? Young planetary systems can be chaotic environments. Large planets interact gravitationally with smaller bodies. An asteroid or comet can receive a gravitational kick strong enough to eject it from its home system. Once it escapes, it may never return. The object becomes an interstellar wanderer. For a very long time, it travels between the stars. Eventually, another planetary system gets in its way. In this case, that system is ours. The object then enters the solar system on a path that does not close into a normal orbit around the Sun. After passing through, it will continue outward. This means humanity gets only one opportunity to observe it. That makes ground-based observatories, space telescopes, and future surveys extremely important. Every additional observation improves our understanding of its orbit. And better orbital calculations can also determine whether the object presents any danger to planets or spacecraft. The good news is that dramatic headlines about an imminent collision should not be confused with scientific predictions. An object's calculated trajectory is not based on a single image or rumor. Researchers combine observations from multiple telescopes and use established gravitational models to determine its path. Uncertainty decreases as more observations are collected. This is how astronomers distinguish a genuine threat from an exciting but harmless flyby. And that brings us back to Mars. Mars is an important target for planetary science because humanity has already placed numerous spacecraft around and on its surface. Orbiters study its atmosphere and geology. Rovers investigate ancient rocks. Landers have measured conditions on the surface. These missions are helping scientists understand whether Mars was once warmer and wetter, and whether it may have possessed environments capable of supporting microbial life in the distant past. An interstellar comet passing through the solar system gives researchers another opportunity to study how material moves between planetary systems. In theory, natural impacts can transport molecules and other material from one world to another. This general concept is connected to ideas such as panspermia. But there is a huge difference between saying that material can move through space and claiming that an object contains engineered organisms or an extraterrestrial message. There is currently no reliable evidence that 3I Atlas is an artificial spacecraft. No confirmed observation has demonstrated controlled propulsion. No verified communication signal has established an intelligent origin. And unusual chemistry, by itself, would not prove artificial design. Science requires evidence that survives attempts to find ordinary explanations. That is why the real investigation is so interesting. Researchers do not need to assume that something is alien technology. They can simply ask what the data actually shows. Does the object's trajectory match gravitational predictions? If not, can natural outgassing explain the difference? What molecules are present? How does the coma change as solar heating increases? What is the object's approximate